Most homeowners think they're protecting their pipes by setting their thermostat to 60 degrees when they leave for vacation. But here's the problem. That's actually 5 degrees too low, and it's causing thousands of dollars in water damage every winter. The magic number is 55 degrees minimum, but there's a specific reason why this temperature matters that most people don't understand. What happens inside your pipes at 54 degrees versus 55 degrees will shock you, and I'm about to show you the science behind why this 1 degree difference can make or break your home's plumbing system. The logic behind setting your thermostat to 60 degrees makes perfect sense on paper. Water freezes at 32 degrees, so maintaining any temperature above that should protect your pipes. This reasoning works for a glass of water sitting on your kitchen counter, but your plumbing system operates under completely different thermal conditions that most homeowners never consider. Your pipes don't exist in the same temperature environment as your thermostat. While your living room maintains a comfortable 60 degrees, the pipes running through your exterior walls experience a dramatically different thermal reality. These pipes lose heat through conduction, where the cold exterior wall materials actively pull warmth away from the water inside. This heat transfer happens continuously, creating temperature zones around your pipes that can drop 15 to 20 degrees below your thermostat reading. The physics behind this temperature differential involves thermal bridging, where building materials like metal studs and concrete create pathways for cold to penetrate your walls. Your copper or PEX pipes become part of this thermal bridge system, conducting heat away from the water inside toward the colder exterior surfaces. This process accelerates when outdoor temperatures drop below 20 degrees, causing the temperature around your pipes to plummet even faster than the surrounding air. Smart thermostats equipped with remote sensors reveal this hidden temperature problem that traditional thermostats miss completely. These sensors placed near pipe locations often show readings that are 10 to 15 degrees lower than the main thermostat display. A home with a 60-degree thermostat setting might have pipe zones hovering at 45 degrees, putting them dangerously close to the freezing threshold. Real-world examples demonstrate this temperature gap in action. A homeowner in Minnesota left for a week-long vacation with their thermostat set to 59 degrees, confident in their pipe protection. Their smart thermostat recorded basement pipe zones dropping to 28 degrees during a cold snap, resulting in 3 burst pipes and $8,000 in water damage. Meanwhile, a neighbor who maintained 55 degrees with sensor monitoring never experienced temperatures below 40 degrees in their pipe zones. The critical temperature difference between 54 and 55 degrees isn't arbitrary marketing from heating companies. This 1 degree buffer accounts for the thermal lag that occurs when your heating system cycles on and off. During the off-cycle periods, pipe zones can drop 5 to 8 degrees below your thermostat setting before the heating system engages again. Starting from 55 degrees gives you the thermal cushion needed to prevent these cyclical temperature drops from reaching the danger zone. Temperature fluctuations compound this problem through thermal expansion and contraction cycles. When pipe zones repeatedly drop toward freezing and then warm up again, the constant expansion and contraction weakens pipe joints and fittings. This process creates microscopic cracks that turn into major failures when temperatures finally drop low enough to cause actual freezing. The 55-degree minimum rule specifically addresses these thermal dynamics by maintaining pipe zone temperatures above 40 degrees, even during heating system off cycles. This temperature floor prevents both immediate freeze damage and the gradual weakening that occurs through repeated thermal cycling. Smart thermostats can monitor these pipe zones continuously and alert you when temperatures approach the critical threshold, giving you time to adjust your heating settings before damage occurs. Professional heating contractors use thermal imaging cameras to map these temperature variations throughout homes, revealing cold spots that homeowners never suspect exist. These thermal maps show pipe locations where temperatures drop most dramatically, usually in exterior wall cavities and unheated basement areas. The visual evidence demonstrates why thermostat readings alone provide insufficient protection for your plumbing system. This temperature misconception connects directly to other pipe protection mistakes that homeowners make when they assume simple solutions will handle complex thermal problems. Most homeowners disconnect garden hoses thinking they're protecting the hose from cracking in freezing temperatures. This assumption misses the real danger entirely. That connected hose creates a closed hydraulic system that transforms your outdoor faucet into a pressure bomb capable of destroying pipes throughout your entire home. When water freezes inside a connected hose, it expands with tremendous force, generating pressure that has nowhere to escape. This isn't the gradual expansion you might imagine. Ice formation creates sudden pressure spikes that can reach thousands of pounds per square inch within the closed system formed by your hose, faucet, and connected plumbing lines. The pressure doesn't dissipate harmlessly like most people expect. This hydraulic pressure buildup follows the path of least resistance, traveling backward through your outdoor faucet and into your home's main water lines. The pressure wave moves through your plumbing system like a destructive force, seeking weak points where it can release its energy. Your pipes, joints, and fittings become targets for this concentrated pressure that originated from something as simple as a forgotten garden hose. The pressure transmission happens faster than most homeowners realize. Within minutes of ice formation in the hose, the pressure wave can reach pipe joints located deep inside your walls. These joints represent the weakest points in your plumbing system, designed to handle normal water pressure, but not the extreme forces generated by expanding ice. The pressure finds these vulnerable connections and exploits them with devastating results. Even frost-proof outdoor faucets fall victim to this pressure backup system. These faucets move the shutoff valve inside your heated home to prevent freezing, but they can't protect against the hydraulic pressure created by a connected hose. The pressure travels through the frost-proof mechanism and into your interior plumbing lines, where it causes the same destructive failures that occur with standard outdoor faucets. The most expensive damage occurs at pipe joints inside your walls, particularly at elbow connections and T-fittings, where multiple pipes converge. These joints typically fail first because they experience stress concentration from multiple directions. When these interior joints burst, water floods the space inside your walls, requiring extensive drywall removal, insulation replacement, and structural repairs that can cost thousands of dollars. Periodic checking throughout winter provides false security because temperature fluctuations create freeze-thaw cycles that gradually weaken your entire plumbing system. Each cycle of freezing and thawing in the connected hose stresses the pipe joints slightly more. The damage accumulates over multiple cycles until a joint finally fails, often during a mild temperature swing when homeowners least expect problems. The freeze-thaw process creates microscopic cracks in pipe joints that expand with each subsequent freeze cycle. These cracks remain invisible until they reach critical size and cause sudden catastrophic failure. A joint that survived 10 freeze-thaw cycles might fail completely on the 11th cycle, making the timing unpredictable and dangerous. Temperature monitoring equipment reveals the shocking speed of this pressure transmission. Sensors placed at various points throughout plumbing systems show pressure spikes reaching interior pipes within 5 to 10 minutes of initial ice formation in connected hoses. The pressure doesn't build gradually over hours or days. It strikes with sudden force that gives homeowners no opportunity to intervene. Disconnecting hoses eliminates the closed pressure system entirely, allowing any ice formation to expand harmlessly outward instead of creating destructive internal pressure. When water freezes in a disconnected hose, the ice simply pushes outward through the open end, releasing pressure safely rather than transmitting it backward into your home's plumbing system. This pressure principle extends beyond garden hoses to other outdoor water fixtures that create similar closed systems when left connected during freezing weather. Most homeowners assume their garage pipes stay protected because the garage feels warmer than outside temperatures, and they figure a quick 10-minute project won't create any freezing risk. This assumption ignores the reality that garage pipes receive minimal insulation compared to your main house plumbing, making them vulnerable to rapid temperature changes that can cause freezing damage in surprisingly short time periods. Garage construction creates thermal bridges that conduct cold directly to pipe locations through uninsulated wall cavities and ceiling spaces. Unlike your main house where insulated walls provide thermal barriers, garage walls typically contain minimal insulation that stops at the living space boundary. The metal studs and concrete surfaces in garage construction act as thermal conductors, pulling cold from outside surfaces directly to pipe locations with no insulation buffer to slow the heat transfer process. Cold air creates convection currents that target vulnerable pipelines within minutes of opening your garage door. These currents flow along garage ceiling lines where water pipes are commonly routed, creating direct contact between freezing air and exposed pipe surfaces. The convection effect accelerates as cold air enters through the open door and rises along the warmer ceiling surfaces, creating circulation patterns that continuously bathe pipe locations in cold air. Projects that seem like they'll take 10 minutes often stretch to 30 or 45 minutes, creating extended exposure periods during critical temperature windows. You start a simple task like organizing tools or loading equipment, but distractions and complications extend the time far beyond your original estimate. Meanwhile, the cold air circulation continues working on your exposed pipes, dropping their temperature steadily toward the freezing point without any obvious warning signs. The specific pipe locations in garages that freeze first include lines running to outdoor spigots and secondary bathroom connections. These pipes often run along exterior walls where cold penetration is highest, and they typically carry smaller water volumes that freeze faster than main supply lines. The outdoor spigot lines are particularly vulnerable because they connect directly to exterior faucets, creating thermal pathways that conduct cold from outside surfaces directly into your garage pipe system. Secondary bathroom connections freeze next because these lines often run through unheated spaces before reaching the heated bathroom areas. The pipe sections in the garage represent the most exposed portions of these runs, where cold air can access them most directly. These connections also tend to have lower water flow rates than main supply lines, allowing cold temperatures to penetrate the water inside more quickly. Even temperatures above freezing can cause problems when combined with wind chill effects that penetrate open garage spaces. A 35-degree day with 20-mile-per-hour winds creates effective temperatures well below freezing for exposed pipe surfaces. The wind chill doesn't just affect the air temperature, it increases the heat transfer rate from your pipes to the surrounding air, causing them to lose heat much faster than they would in calm conditions. The wind effect becomes particularly dangerous when it creates sustained air movement across pipe surfaces. Still, air provides some insulation value, but moving air continuously removes the thin layer of warmer air that normally surrounds pipe surfaces. This constant air movement accelerates the cooling process, causing pipes to reach freezing temperatures even when ambient air temperatures remain above 32 degrees. Temperature monitoring in garages reveals how quickly pipe temperatures drop once cold air circulation begins. Sensors placed on garage pipe surfaces show temperature drops of 10 to 15 degrees within the first 15 minutes of opening garage doors during cold weather. The cooling continues at a steady rate, with pipe temperatures reaching critical levels within 30 to 45 minutes of sustained cold air exposure. Developing the habit of closing garage doors before starting any project eliminates the thermal convection that rapidly chills pipe zones. This simple practice prevents the cold air circulation that creates rapid temperature drops in pipe locations. The closed garage maintains a thermal buffer that slows heat loss from pipe surfaces, giving you protection time that open doors eliminate completely. This rapid cooling principle affects other areas of your home where warm air circulation becomes critical for protecting vulnerable pipe locations from temperature drops. This method appears to be an old wives' tale that couldn't possibly make a significant difference in pipe protection. Opening cabinet doors under your sink seems far too simple to prevent serious freezing damage, especially when compared to expensive insulation solutions or high-tech monitoring systems. The concept sounds like folklore passed down through generations rather than legitimate engineering advice. Cabinet spaces create dead air zones where cold drafts accumulate, and these spaces often contain the most vulnerable pipe sections in your home. These enclosed areas function like cold air traps, collecting frigid air that seeps through building penetrations and holding it in direct contact with your water lines. The cabinet structure itself prevents natural air circulation, creating stagnant pockets where cold temperatures concentrate around pipe surfaces. Closed cabinets trap cold air that seeps through exterior wall penetrations, creating microclimates that can be 10, 15 degrees colder than room temperature. Cold air enters through gaps around pipe penetrations, electrical outlets, and construction joints in exterior walls. Once inside the cabinet space, this cold air becomes trapped with nowhere to escape, gradually building up density and dropping temperatures around your pipes. Temperature measurements inside closed cabinets reveal shocking temperature differentials that homeowners never suspect exist. The specific air circulation patterns that occur when cabinet doors open demonstrate how warm air displacement prevents cold air accumulation. Opening the doors allows heated room air to flow into the cabinet space, creating convection currents that push cold air out and replace it with warmer air from your living space. This circulation process continues as long as the doors remain open, maintaining consistent air exchange that prevents cold air from settling around pipe locations. Under-sink areas are particularly vulnerable because they're located on exterior walls where cold penetration is highest. kitchen and bathroom sinks are typically positioned against exterior walls for plumbing convenience, placing the associated pipes directly in the path of cold air infiltration. These locations receive the most direct exposure to outdoor temperatures through wall conduction and air leakage, making them prime targets for freezing damage when cold air becomes trapped inside closed cabinets. Thermal stratification occurs in closed cabinet spaces, where cold air settles at pipe level while warmer air remains trapped above. Cold air is denser than warm air, causing it to sink to the bottom of cabinet spaces, where water pipes are typically located. The warm air stays near the top of the cabinet, creating a temperature gradient that leaves pipes in the coldest zone. This stratification effect intensifies over time as more cold air accumulates in the lower portion of the cabinet space. The cabinet door technique works best when combined with thermostat fan settings that maintain consistent air circulation throughout the home. Setting your thermostat fan to on instead of auto creates continuous air movement that helps push heated air into cabinet spaces and prevents dead air zones from forming. The constant circulation ensures that warm air reaches pipe locations consistently, rather than only when the heating system cycles on. Professional thermal imaging reveals the dramatic temperature differences that occur between open and closed cabinet configurations. Cameras show pipe temperatures dropping 8–12 degrees within closed cabinets compared to open cabinet temperatures during the same conditions. The visual evidence demonstrates how cabinet doors create thermal barriers that trap cold air against pipe surfaces. Opening cabinet doors allows heated air to reach pipe zones and prevents the cold air accumulation that causes localized freezing. This simple action eliminates the dead air zones that create dangerous microclimates around your pipes. The continuous air exchange maintains pipe temperatures much closer to room temperature, providing effective protection against freezing damage. This air circulation principle applies to other hidden areas where pipes are vulnerable to temperature drops, including utility closets, crawl spaces and basement storage areas where similar dead air zones threaten pipe integrity. Standard faucet covers seem like the obvious solution since they're specifically marketed for freeze protection and sold in every hardware store during winter months. The marketing makes them appear foolproof, with bright packaging that promises complete protection against freezing temperatures. Most homeowners grab these covers assuming they've solved their outdoor faucet protection needs with a simple $5 purchase. These covers only protect against light frost, and during hard freezes they can actually make the problem worse by trapping moisture. The foam material absorbs water from rain, snow, and humidity, creating a soggy barrier around your faucet. When temperatures drop below freezing, this absorbed water turns to ice, creating an insulated shell that holds cold temperatures directly against your faucet. As one expert explains, if you wrap your faucet with anything that absorbs water, the material will freeze along with your pipe, and with your faucet cover, it will make it worse by insulating the cold inside like a freezer. Basic faucet covers don't address the critical vulnerability point, the rubber washer area where water actually shuts off inside the faucet body. This internal component represents the most freeze-susceptible part of your outdoor faucet system. The covers focus on insulating the exterior spout and handle, completely ignoring the internal mechanisms where actual freeze damage occurs. The part of the faucet that truly needs protection is this part right here, referring to the washer location that standard covers leave completely exposed. Foam insulation tubing wrapped with duct tape creates a superior seal that prevents both air infiltration and moisture accumulation. This method addresses the specific failure points that standard covers miss. The foam tubing provides insulation value while the duct tape creates a waterproof barrier that prevents moisture from penetrating to the vulnerable internal components. Unlike standard covers that allow air and moisture movement, this combination creates a complete thermal and moisture barrier around the entire faucet assembly. Frost-proof silcocks solve the problem completely by moving the shutoff valve inside the heated building space, eliminating the outdoor vulnerability entirely. These specialized faucets relocate the critical rubber washer component from the outdoor faucet body to a position inside your heated home. The vulnerable shutoff mechanism doesn't exist back there, it's here way back inside the building where it can't freeze. This design change eliminates the fundamental weakness that causes standard outdoor faucets to fail during freezing weather. The installation differences between standard outdoor faucets and frost-proof silcocks center on the internal valve placement that changes everything about freeze protection. Standard faucets position the shutoff valve within the outdoor faucet body, where it remains exposed to exterior temperatures. Frost-proof sillcocks extend the valve stem through the wall, placing the actual shutoff mechanism in your heated interior space. This valve relocation means the critical component stays at room temperature regardless of outdoor conditions. Even professional-grade insulation can fail if it absorbs water, which then freezes and creates worse conditions than no protection at all. High-quality insulation materials lose their effectiveness when they become saturated with moisture. The absorbed water conducts cold temperatures directly to pipe surfaces, while the wet insulation provides no thermal barrier. Standard covers are not waterproof, and water can migrate inside, leading to freezing conditions that damage both the insulation and the faucet components. Professional installation reveals that moisture management matters more than insulation thickness for outdoor faucet protection. Waterproof barriers prevent the moisture accumulation that destroys insulation effectiveness. Even thick, expensive insulation becomes counterproductive when water penetrates and freezes within the material. Frost-proof sillcocks eliminate outdoor freezing points entirely, while proper foam insulation with moisture barriers protects standard faucets during severe weather. The sillcock design provides permanent protection by relocating vulnerable components, while the foam and tape method creates effective temporary protection for existing standard faucets. This moisture and insulation principle applies to other outdoor water systems that homeowners often overlook, including underground drainage components where water retention creates similar freeze vulnerabilities. Most homeowners focus on visible pipes and ignore the underground drainage systems that can cause just as much damage when they freeze. Your downspout drainage system includes underground pipes that most people never think about until water starts backing up into their foundation or basement. These hidden components carry rainwater away from your home, but they create freezing vulnerabilities that can cause thousands of dollars in water damage. Underground downspout pipes hold water that can freeze into solid ice blocks, creating backups that flood foundations and basements. After rain events, water remains trapped in these underground sections, creating perfect conditions for ice formation during temperature drops. The standing water freezes into solid barriers that block normal drainage flow, forcing water to back up through the system and find alternative escape routes. This backup water often emerges around your foundation, creating flooding conditions that damage basement walls and compromise structural integrity. Proper slope design allows water to drain completely from underground pipes, preventing the standing water that creates freeze problems. The fundamental principle involves installing pipes with sufficient slope to facilitate complete water evacuation after every rain event. This design eliminates water pooling within the pipe system, removing the source material that forms destructive ice blocks. The slope creates gravitational flow that pulls water completely through the underground sections, leaving dry pipes that cannot freeze regardless of temperature conditions. The 1% slope requirement ensures complete drainage after rain events, eliminating the water retention that causes freeze-ups. This standard means creating a 1-inch drop in elevation for every 100 inches of horizontal pipe run. The specific slope calculation provides enough gravitational force to move water consistently through the underground system without creating excessive flow velocities that cause erosion problems. Implementing this precise slope measurement is critical for long-term system functionality and protection against freeze damage. 3-inch pop-up emitters enhance drainage compared to 4-inch emitters because the smaller elbow holds less water, allowing remaining water to drain more quickly. The reduced water retention in 3-inch systems creates faster evacuation times that minimize freezing opportunities. Strategic knife cuts in the pipe allow water to leach into surrounding soil, providing additional drainage pathways that prevent water accumulation within the pipe system. These modifications work together to minimize water retention and improve system resilience against freezing conditions. Heat tape works for downspouts themselves, but isn't necessary for underground sections when proper drainage techniques are implemented. The visible downspout sections above ground benefit from heat tape protection because they remain exposed to freezing air temperatures. Underground sections stay protected by soil temperature stability and proper drainage design that eliminates standing water. The combination approach uses heat tape where needed while relying on engineering solutions for underground protection. Pipe diameter affects drainage speed, with 3-inch systems draining faster than 4-inch systems in freeze-prone areas. The faster drainage reduces the time water remains in pipes, decreasing opportunities for ice formation during temperature drops. This drainage speed advantage becomes particularly important in regions with frequent freeze-thaw cycles where rapid water evacuation prevents ice buildup that creates system blockages. Drainage basins are not recommended because they hold too much water, increasing freezing risk. These basins accumulate significant water volumes that freeze into large ice blocks, creating major system failures. Proper slope and drainage modifications provide more effective freeze prevention compared to drainage basins, which become significant failure points in cold climates. Soil type affects drainage effectiveness, with clay soil perking water more slowly than other soil types. Clay soil areas require more aggressive drainage modifications, including additional knife cuts to ensure effective water removal from underground pipes. The soil permeability directly impacts how quickly water leaves the pipe system and enters surrounding ground. Proper underground drainage design eliminates standing water that can freeze, while heat tape protects visible downspout sections above ground. These drainage principles connect to overall water management strategies that prevent freeze damage throughout your property by addressing both visible and hidden water system vulnerabilities. The difference between pipes that survive winter and those that burst isn't about expensive solutions. It's about understanding the specific physics of how cold actually reaches your water lines. Cold attacks through thermostat gaps, hydraulic pressure from connected hoses, convection currents in open garages, dead air zones in closed cabinets, moisture-trapping faucet covers, and standing water in underground drainage systems. Every technique we've covered addresses a different pathway that cold uses to attack your plumbing system, and combining them creates comprehensive defense that most homeowners never achieve. Start implementing these strategies before the next cold snap, because prevention costs far less than water damage restoration.